And we arrive at the last lesson of the semester. This one is also about integrating in some strange and different ways. But I think this lesson's a little bit interesting because what this lesson starts with is, I'm going to keep this on the side here so I can come back to it quickly. It starts with the idea that some things start to form patterns the more you integrate. And when we recognize some of these patterns, here's an example of a pattern that occurs. If you have x ln of x, we can decide that this one is best integrated by parts. You can do that integration on your own if you want. If I have ln of x over x, this one can be done by a u substitution by saying u is equal to the ln of x. The du's will cancel, and then you'll get something that actually looks very similar to this if I have 1 over x ln of x dx. And in this case, I would actually also say that u is equal to ln of x, because you still have that same 1 over x piece that's going to cancel. But if I just make a subtle alteration to make it x over ln of x dx, this integral is not an elementary function, meaning it would have to use techniques of approximations similar to what we did before. And when we say not an elementary function, I mean this is the simplest way to express the integral. There is no other simpler way to do it. It's kind of a weird concept to think about, that it exists. We know it exists, but we can't express it in terms of another function. It's just its own thing. But the idea behind a lot of these table elements is that we can derive it once and then use it forever. Derive once and use forever. So that brings about these tables. And these tables are not necessarily as straightforward as you think they are, but these tables occur in the back of your book in a section called Appendix B. I have duplicated this section underneath this in OneNote so that you can have just a straight-up copy of it. You don't have to memorize anything on here. It is rather lengthy. You can look at the table organization and see that there are forms involving, well, I'm going to kind of write some of these down here. But you have different forms that occur, forms involving u to the n, a plus bu, and so forth. And these, well, we can say that the classifications of these occur in very, very specific ways. And as you move through these tables, you can see the different forms that can happen. For instance, these are quadratics. These are radicals. Move through, you have the sum and difference of squares. You have the radical of the sum and difference of squares. You have forms involving sine and cosine and tangent and so forth. Inverse trig, exponentials, natural logs, hyperbolics, some function types that you may not even quite understand yet. But those four pages are very much what we're looking for. So you're going to have access to this table structure on a quiz. I've already made the quiz and copied. The first 2 pages are rippable, and you can just use this. So you don't have to bring anything with you into that. And you should have this nearby. Have a copy of it, maybe print off a copy, but have it when doing these problems. Everything in here can be verified. I'm asking you to accept them because the verification is beyond the scope of what this lesson is going to do. I'm not asking you to verify these formulas. You can. They are all done using techniques that we could possibly do. For instance, if I look at, I'm going to use this F4 notation, this formula 4, which says that the integral of u over a plus bu quantity squared du, that's the same thing as, let's kind of slide this over, 1 over b squared times the quantity a over a plus bu plus the natural log of absolute value of a plus bu, absolute value plus c. Okay, this can be done via partial fractions. If I separate that denominator out, well, not separate it out, but if I just do it based on partial fractions, a plus bu is a linear, it's a repeated linear factor. When we say u, by the way, this is our other function. So the u's themselves, you can think of in terms of x, or you can think of in terms of substitutions where the du cancels something out. That can get a little tricky. Formula 19, for instance, is another one that this is an interesting one to try to do. The book actually says that this one can be verified via parts. I actually had much better success doing a substitution with the radicand. Here, let me finish actually writing it. A plus bu. Notice how I don't have a plus c because there's an implied plus c from this other integral. This type of formula gives another integral as part of it, which maybe then you can do something with that integral. But, oh, that's a u, sorry. This is the problem with writing these things down quickly. So a plus bu, but it's formula 19, so you can take a look at the nice printed version instead of my mucky version. But that, it's, again, your book says it's done via parts. I question that because I was not having great success with parts on this. I was actually having much better success letting something like u equal a plus bx. I have substituted the u for an x in there, and then letting the du be, and go forth with that. It actually makes it a nice partial fractions one. But again, don't feel like you have to. That's beyond the scope of what you need to worry about right now. I'm going to give another example of something like formula 84. So let's flip over to that one. These are just your book's notations. But this is the one that it says 1 over 1 plus e to the u du is equal to u minus the natural log of 1 plus e to the u plus c. And this one can be verified via substitution, where I then let, well, v equal e to the u and dv equals e to the u du. And we can, oh, sorry, not d, my bad. V equal 1 plus e to the u and dv equal e to the u du. We can then reconfigure the entire thing here to be in terms of v's and dv's and go for that. And that's something we've actually done before, but it's just beyond the scope, again, of what we need to do at this point. So all I want you to do, notice with this, is just there's a table of these templates. And I want to think of them more like templates for how integrals can go. These are things that you would have proved once, and some of the computers out there, the people, would have looked up, and they would have had access to this to try to get whatever they would need. And the classifications of these are all based on these systems here. So I'm not going to write down what the classifications are. You can look them up. And again, you're going to have access to this Appendix B. But let's work some examples of how this is going to play out. So, for example, I want you actually in this section to use the tables. I don't want you to reinvent the wheel. I want you to pretend like this wheel has been invented for you. And what I get is something underneath a radical, and I want to identify that that thing underneath a radical is linear. So if we start scanning the section on linearity, which would be things like, okay, so here's a section on linear, but if I scroll down, there's a section on radical linear. I get a form. I look at these forms. Number 17 is looking pretty suspect. And so if I consider formula 17, which is du over u radical a plus bu is equal to, and I'm going to write this whole thing down. I'm actually going to use, I guess there's two versions that you can go with, which you can prove later that they're both the same thing. I'm going to use the 2 over root negative a arctangent of root a plus bu over negative a. I'm going to use this one because this is the one where a is less than 0. And I know that a is less than 0 because if I try to piece together this compared to this, I can see that this works if a is equal to negative 1 and b is equal to 1. And then I also would want to say that u is equal to x, which then means that du is equal to dx. And those would be all the substitutions I make. If a was greater than 0, we'd want to use the other natural log form. I didn't neglect to see that on this side of the screen, but okay, now I see it. So now we go ahead and we don't really do anything. This is actually stupidly easy. It's a little bit of a matching game. And if you get this right, this is sort of a little Christmas present to you. Okay, so 2 over, substitute, negative a would give me root 1 arctangent of radical negative 1 plus x over negative 1 plus c, or just quite simply 2 arctangent of radical x minus 1. Oh, I can make that a bigger radical x minus 1 plus c. And that's it. You wouldn't have had to do much except know that that's what the radical matched and looked like, and that would have been a lot quicker than having to reinvent the wheel every single time. So let's keep doing this. I'm going to give you one. If you want to be adventurous, pause the video, see if you can find something that matches what this type is, and then we'll check back in and see if you found it. Pause now. And if you're resuming, we can see that this is a form involving, I think it's involving sort of a sum or difference of squares. There's this x on the outside, so we have to get a little crafty. And if I say let u equal x squared, du could be 2x dx. And I'm going to change this whole thing around to say that now this is the same thing as the integral of, let's pull the 1/2 out, and I get radical u squared minus 9 du, which that matches this number 26, which I feel like I want to write here. 26, or formula 26, is radical u squared plus or minus a squared du, integral, and that is, is that the one I want? Yeah, and that is equal to 1/2 u radical u squared plus or minus a squared, then plus or minus a squared natural log of absolute value of u plus radical u squared plus or minus a squared absolute value close parentheses plus c. Whew. Okay, note that the plus minus matches. So if one is plus, the other is plus. This is where that minus plus may come into play in some of these formulas. Okay, so in any case, we already have u equals u. I'm just going to let a equal 9, or a equal 3, and let's just plug it in. Kind of fun. You get 1/2 times u was x squared. Then you have the same x to the 4th minus 9. Still have a minus. Then you have a squared, and we said a is 3, so that is 9 natural log absolute value of x squared plus radical x to the 4th minus 9 and absolute value, close parentheses, plus c. And that's it. Okay, same thing. Let's see if we can find another one. So this is going to be the integral. This is a definite integral, so we're going to have a little bit more fun with this, of x over 1 plus e to the negative x squared dx. Sorry, that is an x in the numerator. I need to make sure I'm on do not disturb. I don't want to get text from people. Okay. So here we go. You should be able to recognize first, before you decide on a u or anything like that, that I would kind of expect you to see that that thing's going on. So if I let u equal negative x squared, du is equal to negative 2x dx, which means I'm going to pull that negative 1/2 out and change my limits from 0 to 2 to 0 to negative 4. The x's cancel, and I get 1 over 1 plus e to the u du. I'm going to make one more alteration, which is to switch the order of the limits. So then I get 1 over 1 plus e to the u du. And looking for forms involving sine, involving exponentials. 84 looks pretty on target. 84, formula 84 says the integral of 1 over 1 plus e to the u du is u minus ln of 1 plus e to the u plus c. So that becomes our integral. And taking all of this and evaluating it from negative 4 to 0 gives me, forgot the 1/2. So we still have a 1/2 out. Well, that's not formula 84, but we still have a 1/2 outside of this thing from there. We still have a 1/2, then I get a 0 minus the ln of e to the 0, so this would be the ln of 2. Then minus, plugging a negative 4 in, minus the ln of 1 plus e to the negative 4. 1, 2, 3. Okay. So simplifying, I get a negative 4. I get a negative ln of 1 plus e to the negative 4. And I get a minus natural log of 2. And we can just leave it like that. It's not really much simpler if you distribute the negative 1/2, or the 1/2. So that is done. Okay, continuing on, a couple more examples. Actually, 3 more. show what this looks like with sine. So this is an interesting case where if I look at the sequence of how this plays out, I'm going to start by finding ones with sine. So if I go to sine, and I see that we have something like u sine of u du for 52, but then formula 54 is much more applicable. Formula 54 says the integral of u to the n sine of u du is negative u to the n cosine of u plus n integral of u to the n minus 1 cosine of u du. So we kind of have to ascribe that n is equal to 3 here. The rest of it's all the same. So this integral now becomes negative, I guess I could say u is equal to x, a negative x to the third cosine of x plus 3 integral x to the 3 minus 1 is 2 cosine of x dx. But this can go further. Yes, we're doing a little Inception style with this. So if I slide over, I see a very similar type of formula on number 55. Formula 55 says that the integral of u to the n of the cosine of u du becomes u to the n sine of u minus n integral u to the n minus 1 sine of u du. So we're going to keep applying this, negative x cubed cosine of x plus 3, and then this whole thing becomes x to the 2 sine of x minus 2 integral x sine of x dx, which now means that we have this thing. So we get to slide back over, and there is one more left, formula 52. Formula 52 says that the integral of u sine u du is the sine of u minus u cosine of u plus c. So keeping this whole thing present, negative 3 cosine of x plus 3x squared sine of x minus 6. Then I have the sine of x minus x cosine of x and plus a c. And if I configure this all in a nice descending order, I get negative x cubed cosine of x plus 3x squared sine of x plus 6x cosine of x minus 6 sine of x plus c. You're probably looking at me and thinking, why didn't we just do integration by parts at the start with tabular method? I would agree. Of course, tabular method's easier. But that was a simplistic example of one where it could very easily get more complicated. So I just want you to see the method and how repeated iterations could be used. Okay, another example of a repeated iteration. So let's go with the radical 3 minus 5x over 2x dx. So if I take a look at what's happening with this one, we've got a couple of formulas that may play out. Let's look at the radical linear ones. Let's go back to the front. I've got a radical over an x, and if I'm looking at these radicals over x, oh, that's not there. I was looking, here's the ones involving the radicals. 16, 17, 18, nope. Slip over 19, yeah. 19 looks good. With 19, I can take the 2 out and make this an integral of 1/2. And, well, let's not write that down yet. I'm going to write down formula 19 just to be clear. This is the integral of a plus bu over u du is 2 times the same radical plus the integral a times the integral of 1 over u root a plus bu du. Okay, we can do this. B would be -5 and a would be 3. And if that holds up, also u is equal to x. So I'm going to pull the 1/2 out, and let's just do this straight up substitution. So 1/2 times 2 root 3 minus 5x plus 3 radical 1 over x root 3 minus 5x. And that actually slides this whole thing down to the denominator, which then means we get to go again. We scan for another formula. And let's see, one's involving x in the denominator, or this whole thing in the denominator. So let's flip back over. 17 and 18 look good. Actually, 17 looks really good. Formula 17 says that the integral of 1 over u root a plus bu du is, oh, it does that split again. Actually, we already used formula 17. This time, let's see, my a value, and a is the coefficient of, this time a is positive. A is the coefficient of that. A is 3. So since a is positive, we're going to go with the top one. That's equal to 1 over root a, natural log, absolute value, big fraction, radical a plus bu minus radical a over radical a plus bu plus radical a, close absolute value, plus c. So if this is the formula, I'll put it in brown. I'll skip back over to black. We can distribute the 1/2 in, which is going to give me a root 3 minus 5x plus a 3/2 from the 1/2 times the 3. Then we still have the same a's and b's, so I'm going to plug those in. 1 over root 3 ln absolute value, the same radical 3 minus 5x minus radical 3 over 3 minus 5x radical plus radical 3, close, plus c. And it's annoying. We're going to rewrite this entire thing just to deal with this simplification that can happen there. I know. 3 minus 5x in a radical plus root 3 over 2 ln, big absolute value, 3 minus 5x minus root 3 over root 3 minus 5x plus root 3 plus c. Okay, last one. This problem tries to exemplify the idea that many times these integrals become reductive, meaning that they just break apart into smaller integrals. And so that was the previous one. I'm getting all kooky on myself. I'm even writing the wrong thing down. We want to do the integral of sine of 2x over 2 plus the cosine of x. Sorry, my point with this one was actually to start to do a little bit of legwork and a little bit of twistiness to get this to look right. If I move over to the sines and cosines part, it doesn't actually completely have one that looks like this. Actually, it doesn't have anything that looks like this. The closest, it might be 57, but even that is, the numerator is not 1. What you should be thinking is you should be thinking of doing some sort of manipulation with this to try to get it into a better form that's going to match this. We know that the sine of 2x is 2 times the sine of x times the cosine of x over 2 plus the cosine of x dx. So if I just pull from that trig knowledge a little bit and let u equal the cosine of x, du would be equal to the negative sine of x dx. That's going to cancel the sign in the numerator right here when I substitute that in. So the 2 is going to pop out as a constant multiplier. The negative is going to pop out. The sign's going to cancel. And you're going to end up with a u over 2 plus u du, which now completely changes the problem to be not a trig one, but just a basic linear one. And if you look back over this u over du thing, formula 3 is looking pretty good. Formula 3 says that the integral of u over a plus bu du is 1 over b squared times bu minus a, natural log, absolute value, a plus bu plus c. So if I just now say, okay, so then a would be equal to 2 and b would be 1, then we can change this whole thing to be negative 2, let's write that in blue, times 1 over b squared, so 1. Bu would be x, because not x. be u, minus 2 ln of absolute value of 2 plus u plus c, and then you can just plug your u's back in and distribute the negative 2. Negative 2 cosine of x plus 4 natural log absolute value 2 plus cosine of x plus c. So have some fun with this. This is the last one. But I want to emphasize this idea before we go, that the purpose of this is to kind of do all the work once and then to use this. And the one last thing that I can leave you with is your calculators. There's a version of that that's the CAS calculator. It stands for Computer Algebra System. This is how a computer algebra system actually works. It analyzes the function you put in and it matches it to an existing template to come up with an indefinite integral. There are very advanced algorithms for this, but this is mostly, your computer doesn't actually do the work. It just matches and outputs something that's predetermined, much like we're going to do in Chapter 9.